before that, he was okay. Let me start again. So, hi everyone. I'm very happy to welcome Huan today to our seminar series. He's a associate professor at Tsinghua University. Before that, he was in Waterloo at the Perimeter Institute and University of Waterloo, right?
Well,
Where
yeah.
he was of Delft, sorry, where
Mm.
he was an assistant professor, and before that, he was already a postdoc at Perimeter Institute in Princeton. And yeah, so he was quite some time away because if I see so correctly, he also did his PhD at Caltech in the US, but after being some time in the US, he decided to move to China. And yeah, he's now here. And today he's going to talk about ringing black holes. So Huanyang, just feel free to start.
Yeah, well, thank you, Hanjo, for inviting me. So I guess today I'll talk about black hole perturbations. So if you have any questions, just please feel free to interrupt me and ask it, ask questions right away. So, okay. So basically, the binary black hole mergers, I assume people are very familiar with that, given the very successful detection like 10 years ago. For these kind of binary black hole systems, we know that if the black holes are far away, we can describe the motion of these two objects by this so-called post-Newtonian formalism. It's just a way to expand your relativity in terms of V over C or G over R, right? So as these black holes are moving close to each other due to gravitational wave radiation, they will collide at some point. At this point, this space-time is highly dynamic and very nonlinear. And then these two black holes merge into one, and then the final black hole quickly settles to let's say, a stationary rotating curve black hole. So at this last stage, this settling down process, we can approximate this process as a stationary black hole spacetime plus perturbations. That's why people can use the so-called black hole perturbation theory to describe the space-time dynamics in this period. It has been quite successful, and it's also one of the central themes in gravitational wave astronomy nowadays, which will be the focus of our discussion today. So I guess I'll start by giving a brief review of the history of black hole perturbation, and then I'll talk about some of these recent developments, and then I'll move towards some of these frontiers, in particular the nonlinear effects of perturbations, and then I'll probably talk about where we are going in the, let's say, next 10 years. Okay, so intuitively, so when we think about a perturbed black hole, the ringing black hole is very much like a ringing bell. So if we hit the bell, we hear the sound, right? So this is because as we strike the bell, we excite different oscillation modes of the bell, and then they interact with air, and then we essentially hear uh, many modes of this bell. So it's essentially the same thing as we collide two black holes, and then right, the space-time is perturbed, and then intuitively we can view the perturbation as a combination of modes of that space-time, right? So this will help us to understand what's happening as the black hole ringstorm. Um, so to mathematically understand these perturbations of black hole spacetime, I think the pioneering work was given by Ricci and Wheeler in you see 1950s. So at that time, I think we don't have this like phrase black hole invented yet. So you see the paper was talking about the perturbation of a structural singularity. In this paper, they essentially derived the wave equation for the perturbation of a structural black hole with odd parity, and later on, Frank really derived the perturbation in the even parity case. So the combination of these two works essentially together they describe the perturbation of a structural black hole, right? And later on, when people look at the perturbation of rotating black hole, right, it's quite a miracle that if you write down the wave equation, it's still separable. So this is work done by Satokosi in the 1970s, as he derived the wave equation using Newman-Penrose formula. It nicely separates in, for example, in theta and r directions. This allows people to solve equations relatively easily. So with this description of wave equations, some people can uh, like mathematically understand what's going on in a perturbed black hole space-time, right? So one intuition one can get is that if you look at a perturbed black hole, it's similar to a case with light trapped in a imperfect cavity. So it's like here, so the cavity is leaking. So if you have light trapped within the cavity, it leaks out, and then in time the amplitude decreases. So, but if you want to describe the light field within the cavity, it's you can still describe it as something like e to the minus I omega t, where omega here has to be complex because of the leaking. So if we look at this leaking black holes, because the wave can either go to infinity and or towards the horizon, so they will not stay near the black hole forever. So these modes of the black hole are very similar to the modes of this imperfect cavity. So they are usually called quasi-normal modes, not normal modes because they have complex frequencies. So it's quasi-normal modes. And mathematically, if you write down the wave equation, so it's something schematic like this, right? So you have a potential barrier, and then you're trying to solve a eigenvalue problem for the wave by imposing the condition that the wave has to go out towards infinity or go into the horizon. So this is a standard eigenvalue problem. Detweiler and Chandrasekhar solved this problem, right, for the first few modes of short black hole in the 1970s. This kind of eigenvalue problem is also similar to what we were familiar in studying hydrogen atoms in quantum mechanics. So when we look at the energy levels and wave functions of hydrogen atoms, we know that once we write down the Schrodinger equation, we have to separate out the angular wave functions, and then we solve the radial wave function. At the end, these wave functions are characterized by a few so-called quantum numbers, like L and M, characterize the quantum number in the angular directions, and there's another N quantum number characterizing the radial wave functions. So for black holes, it's very similar. So we also have these well, quantum numbers characterizing the angular functions of black hole perturbations, and then the overtone radial overtone number characterizing the radial wave functions for these eigen value problems. As I said just a minute ago, the first few modes with low L and M were tamed by Detweiler and Chandrasekhar. So nowadays we understand much better in terms of the spectrum of mode spectrum of black holes. So if we look at the Schwarzschild mode spectrum, right? So this is a plot with vertical axis being the decay rate of the mode frequency, and the horizontal axis is the oscillation, the real part of mode frequency. So we can see that the different branches of modes, for example, these red plots, they represent the L equals to 2 branch. So because it's Schwarzschild black hole, the M does not matter. So for the angular direction, we only have one like quantum number, and then we see different class because right. So this one with the lowest decay rate is the overtone is 0. This overtone 1, 2, 3. So this is this is a mode. These are modes with different radial overtones, and then we see different signs like the green cross, etc. These are different L's. So these are L equals 3, 4, 5, 6, and etc. So we understand the mode spectrum. So you may wonder, what can we do with it by measuring mode spectrum? Well, the mode spectrum of black holes are uh, determined by the space-time of the black hole itself. So, I mean, it's a good argument that if you measure the spectrum itself, maybe you can already use that to infer the underlying space-time of a black hole, right? So it's very similar to another area of astronomy as astroseismology, where people measure modes of stars, right? So if you measure different modes of stars, you can actually try to infer the internal structure of stars, the property of stars. Here, if we measure modes of black holes, we can use that to try to infer the geometry of black holes. So this kind of business is called black hole spectroscopy. So basically, we want to measure at least multiple mode frequencies and decay rates as a way to probe the black hole space-time and test the prediction of general relativity. Okay, so that's the understanding in the people already had in past decades. But then, given the observation of LIGO started 10 years ago, we now are having more developments in both theory and in particular data analysis. Um, so for this first event, 150914, we can compute the signal to noise ratio of that this event in the rain down stage is about 8. Okay, so in that for that event there is already one mode that's present. Is quite obvious that it's there, and that is the mode with L equals to 2, M equals to 2, and the overtone equals 0, so it's the least damped mode. So people have tried to use this mode, so you can measure the mode frequency and the decay rates because they're determined by the mass and spin of the final black hole. So you can already use that information to infer the mass and spin of the final black hole. So that's what people did analyzing this particular event. So if you see this purple boundary, so these are the posterior constraints given the rain down part of the data. And for the same event, of course, you also have the in-spiral measurement. From the in-spiral measurement, you can infer the individual component masses, and then you can use that to predict what would be the final black hole mass and spin. So then you got this contour. So you see that the in-spiral contour and the rain down contour overlaps with each other in this range, right? So in other words, they're consistent. And if you decide to combine the information of both in-spiral and rain down, merge rain down, so you get this much smaller contour, which with much better uh, measurement on the final black hole mass and spin. So this is a very nice demonstration what people can do with rain downs. But as I said, if you want to do black hole spectroscopy, ideally you want to have the measurement of multiple quasi-normal modes. So not just the main the strongest two mode, but if you want to measure multiple modes, then the difficulty is that other modes, the subdominant modes, are usually weaker or much weaker than the dominant modes. So if I want to focus, right, on the measurement of modes here in this rain down stage, I want to try to fit uh, the data with some starting time by a set of modes, right, with let's say unknown amplitudes and frequency decay rates. So if I choose my starting time here, I mean maybe my linear approximation of the perturbation is good, but then I'm not using the information in the early part, which seems to have stronger signals. But if I choose my fitting at some earlier times, I'm using more data in the rain down stage, but with the risk of, right, my linear approximation of the perturbation may break down. So this is always a challenge that people started to realize when they try to find subdominant modes. Uh, so in particular, there has been well, heated debates about whether there is already enough evidence for higher overtone modes in the data, right? So there, for example, there work by Gisler et al. And they try to fit the rain down with a combination of overtone modes, like either only the fundamental mode or with up to first, second, or third overtones. So what they try to um, argue is that if they include more radial overtone modes in the fitting, it seems the fitting, let's say, to a numerical relativity rain down waveform seems to improve, right? So you see the mismatch decreases. So that means you use this linear mode combinations captures most of these rain down signal, but these modes are not orthogonal nor a complete basis of the ring down. So there is always risk of fitting other sims into these mode bases. Okay, so that's why people have been arguing about these kind of studies. I mean, there is also studies claiming finding the first overtone in the first event, 150914. In addition to this 2-2 mode, they also claim to find 2-2-1. But again, their arguments why other people think it may not be robust. So I mean, I think it's fair to say that maybe there are some hints of first overtone already in the data, and with better and better sensitivity or larger and larger signal to noise ratio, we will eventually detect the first overtone. I think there's no question we will be able to achieve that. But at the same time, we always, I mean, face this theoretical problem that, like, how do we estimate like the effect of other things, right? Nonlinear or non-modal effects. How do we control these things? We will need to answer these questions before we can confidently say that what we measure is reason why it makes sense. Okay, so I'd like to also mention that for this kind of subdominant mode detection, there is a way that can always help, is that to stack multiple signals. So the idea is quite simple. So if you have different events, let's say each event has a weak 3-3 mode, but then you may imagine you can coherently stack the 3-3 mode from different events, and then they become stronger, right? So, but then the question is, how do you coherently stack them, right? So if you don't know their phase, you add them together incoherently, they may, right, cancel each other instead of amplify each other. So you will need to know its phase or have information about their phase at the beginning. So I think the key here is to use the inspire information to infer the phase of these subdominant modes first, and then use this information to combine different events. So the study we did several years ago shows that if you use that, usually you can achieve a factor 2 or 3 amplification for the signal to noise ratio, let's say for the for 3-3 mode. So this approach is pretty generic. You can use that to look at 3-3, 2-1, other modes, linear modes, or you can use that to look at other signals, like for example the quadratic modes that I will talk about later. Okay. So now let's move on to this frontier, I would say, which is the nonlinear modes. As I try to motivate, we always have the problem that if we try to start the feeding time early, we have nonlinear effects. So, but what are the nonlinear effects, right? Uh, so if you look at Cauchy equation, it's a linear equation. So we will have to think about the wave equations at higher orders. Right? So let's say if we consider wave equation at second order, so at this order, the waves around the black hole, they will interact with each other. For example, if we look at a particular wave at this frequency omega near the black hole, they will interact with itself, for example. And then this interaction can also generate new waves waves with a frequency, let's say 2 omega. So so now suddenly you have a new mode with a different frequency, right? So this 2 omega frequency may never coincide with any of these linear mode frequencies. So it's a new mode due to second order effects. I think the for sure show this was first discussed in 2007 and many later on works. And the key thing here is to write down your wave equation, the second order. You have wave operator operating your at the second order wave, and then it's sourced by the linear waves. So because it's a source time is a bilinear form on the linear waves, so that's why if you have e to the I omega t here, e to the I omega t here, you can generate 2 omega oscillations. So I mean, I think this is intuitively straightforward, but then it's kind of non-trivial uh, to determine the amplitude and phase of these second order quasi-normal modes. I mean, they're according to the equation, they're totally determined by the amplitude and phase of the linear quasi-normal modes, but like the exact number is unknown, and this exact number will essentially reflect how strongly waves interact near a black hole. Okay, I think several years ago there was a workshop at CCA, and later on, people were decided to search for these second order modes in numerical simulations. And so they try to search for from both head-on collisions of black holes and also these quasi-circular mergers of binary black holes. Uh, as I said, so there is a so the second order mode is sourced by the quadratic coupling of linear modes. So you would expect the amplitude of second modes is is a linear mode square, so you can fit the data as you search for that particular quadratic mode, and indeed at infinity you do find this kind of quadratic dependence in both head-on and quasi-circular simulations, and also you can search for the frequency of these new modes. And indeed, it is consistent with twice as the linear mode frequencies. Okay, and so this is the search at infinity. But then you can ask similar questions, right? So if you have wave interacting near the black hole with this nonlinear quadratic effects, does it affect the black hole horizon or not, right? So, um, uh, like, does the black hole horizon deform in a similar way as wave radiated towards infinity? The answer is yes. Okay, so but then you need new tools to describe the deformation of black hole horizons, right? So geometrically, if you look at the horizon, right, you can it is a surface that the light bundle has zero expansion, but then you can look at the shear of these bundles, and then you can try to measure the shear on this black hole horizon, and you can decompose them into multiple moments. So if there is a there is linear mode in the space-time, so that it turns out that the shear of the horizon, I mean, they will have these linear mode dependencies, linear quaternion mode dependencies. But then if you also have non-linearities, like for example, quadratic quaternion mode in the space-time, then you would expect that the horizon share oscillation should also have um, um, new frequency components, right? The two omega components. So that's what we try to search for using head-on collisions of Schwarzschild black holes. It's it's much more difficult than searching for the modes at infinity because you have to really have a lots of resolution near horizon, and but uh, we indeed found these quadratic modes on the horizon as well. So these the modes we recover have has a consistent quadratic relations, and the frequency of the mode indeed matches the predictions. It's two times the linear mode frequency. Um, so another test we did is that as we fit the share on the horizon, we decide that we either use only linear modes to fit the share, or we use one quadratic modes plus linear modes to fit. For example, if we use two modes to fit the two linear modes fit the oscillation, the share. This is this line here. But then if we use one linear modes plus one quadratic modes, I mean in total it's still two modes fit, then you see this dashed line which is below this solid line. So this shows that the mismatch has improved more than one order of magnitude because we have replaced the linear mode by a quadratic mode. So this game can be carried on if you allow to use more modes. Like for example, in total you have three modes. You can either use three linear modes to fit. That's this line, or you can use two linear modes plus one quadratic mode to fit, which is this line. So again, you can see two orders of magnitude improvement in mismatch. Same for four modes. So it's quite evident that the quadratic modes should be there to describe the horizon oscillations. Okay. But theoretically, this just shows the nonlinear mode affect both waves at infinity and the geometry of horizon. But how do we understand them theoretically? I mean, to be able to compute them, like for a generic curved black hole, it's quite non-trivial. Okay, I wrote down some schematically some equation for the Schwarzschild case, but for a curved black hole, you may want to use invariant quantities to describe the wave oscillations, right? You want to expand them order by order in terms of some amplitude parameter. And similarly, they correspond to the expansion of space-time metric order by order, right? So one needs to derive the second order Tagose equation, something like this. The left-hand side is Tagose operator operating on the second order wave variable, but then you also have a source term that's bilinear in the linear wave. So there's one important fact is that these Newman-Compound quantities psi, they're complex valued functions. But if we look at the space-time metric, they're real functions. So if we look at any particular quasi-normal psi, for example, it has a given temporal dependence I omega t e to the I m phi, that's fine. But if we look at the corresponding metric perturbation, it must have a conjugate piece to stay real, right? So if you have I omega t IM5 piece, and must have I minus I omega star T and minus IM5 piece. It must have a conjugate channel. So this turns out to be important as one understands the quadratic couplings. So this is also related to how people classify the linear modes. So if we look at um, for example, for genetic curve black hole, the linear mode families, right? So there is a branch with real positive real frequencies. Okay, so this is real part of the frequency. This is imaginary part of frequency. So if it's Schwarzschild, then for example, 2, 2, and 2 minus 2, they have the same frequency here, but then if you increase the black hole spin, then the degeneracy is broken, right? So the 2, 2 frequency goes in this direction, and 2 minus 2 uh, frequency goes into this direction. But then you see there is another branch, right? As I said, there is a branch caused by this conjugation. It's people sometimes call it a mirror branch. So basically they have opposite real part of frequencies, but the same decay rates. So these two branches are right conjugate or mirrors of each other. We have labels here minus plus, denoting that they have either positive or negative real parts. So these are the classification for linear modes. So to be complete, so when people talk about the L, M, and N for quadratic modes, it's also convenient to add this P factor to denote whether you're looking at this positive branch or negative branch. I mean, they conjugate to each other, but it's important to note that there are two mirror branches. And then if you look at quadratic modes, so you can, for example, some modes with given temporal and angular dependencies. So it turns out that if you think what kinds of linear mode may generate quadratic mode with this given temporal and phi dependencies, it turns out there are different kinds of choices of linear modes. Okay, so I'm listing two, right? So, well, four different linear modes, but then there are like four different channels that they can produce the same temporal and angular dependencies. So these are the details I don't expect you to like understand right away why this is happening, but this is really what I was just trying to explain the conjugation, allow you to have different couplings between these channels, and theoretically there are four channels, but it turns out one of them always have zero coupling coefficient. So essentially you have three channels in operation. And then um, uh, when we try to compute the quadratic mode amplitude, right? So it's generated by the linear mode. So we can divide the linear mode amplitude, divide this quadratic amplitude by this linear mode amplitude. And what we get is a coupling coefficients that's independent of the linear mode amplitude. This is like a universal number that only depends on the black hole spin. Okay, and this can be measured by extracting modes from, for example, numerical simulations. So we have used two different approaches to compute these coupling coefficients, and they match each other. And if we combine these numbers and then combine and to compare with numerical simulations, I mean, the simulations have pretty large error bars, especially for larger spins, but then they're broadly consistent. I think later on Keith Midman, they have better simulations where you can, with small error bars, you can see that the fitting, the agreement is pretty well. The semi-analytical calculation with the fitting from numerical simulations. So it's fair to say that the quadratic modes for rotating black holes is now understood, but this is just one type of nonlinearity. Okay, for this type of nonlinearity, I mean, you can actually look at uh, different kinds of mode couplings, right? So it's you have different, you just pick two linear modes, and I can ask what is the coupling coefficients of these two linear modes and what is the amplitude of the quadratic mode that they generate. So these can be all computed. So we have computed several leading coupling channels and the corresponding amplitudes of the quadratic modes, and we've provided fitting formulas for that. So it turns out that these uh, different quadratic modes can be significant in the sense that they may be detected with gravitational wave detectors. So in this plot here, I'm assuming, for example, two stellar mass black holes, I think it's 50 plus 50, something like that, placed at the distance of around 400 megaparsec. It must be the distance of the first binary black hole event. So if we can choose to tune the mass ratio of the binary or the spin of the binary, and then you can you can predict the amplitude of the quadratic modes for these binaries, and then you can use the sensitivity of Cosmic Explorer, one Cosmic Explorer detector, and you can try to ask what is the corresponding signal to noise ratio. So you can see that for quite some large range of parameters, you get significant more than 10 signal to noise ratio. This is this 2-to coupling. So if you have LISA, you have massive black hole mergers, right? So the total ring-down signal to noise ratio can be very big, right? So more than thousands, several thousands. And in that case, you can predict for example, you have two 10 to 6 black holes merge at the redshift 1, and you can predict what is signal to noise ratio of the quadratic mode. And it's several hundreds can be, okay? So it can be pretty loud. So we should definitely include this effect in the ring down waveform and search for it because it's in the data. Okay. Um, So in the last part, I'd like to discuss a bit what will be happening in the next 10 years that I think. I think important thing is that as we have better detectors, the signal to noise ratio of the events will increase in time. So that will give us the opportunity to measure, right, dominant modes or other non-modal effects in the ring down. So this is actually a golden opportunity for us. Um, I think this also means that maybe we should try to think about beyond black hole spectroscopy. Right? So black hole spectroscopy just means that you want to measure the frequency and decay rates for various quasinole modes, linear quasinole modes. But there are many different effects in the rain down. Maybe we should describe all of them, right? So like for example, in the inspiral stage of a binary black hole evolution, we have this post-Newtonian, post-Minkowski formalism describing the dynamics and the waveform systematically. So maybe we should imagine having a similar thing, a full ring down waveform that systematically describe everything in the ring down. I think it's possible given the tool of black hole perturbation theory. If we can schematically think, the ring down may be expanded in powers of these epsilons, right? So it's a bookkeeping index for the amplitudes, and this just means we can try to solve these perturbations order by order in the with the black hole perturbation theory. So in the linear order, it is known that if we look at the Green's function at the linear order, right? So there are actually three parts. There are these poles of this Green function, which are the quasinole modes that we understand pretty well nowadays. But then uh, there are parts that correspond to this so-called branch card of the Green's function. So these correspond to the wave scattered of this one of our kind of potential. It's called the tail effect, right? So the tail effect also exists in post-Newtonian regime, but then it's the wave scattering at larger distances, but it's there. And then there is another part that, right, so it corresponds to this contour, this semicircle integrate contour here. That's the direct part. So if you have a generic source, you will generate all three kinds of signals, right? So usually the direct part will come first because it's the direct like cone piece. You arrive first, and then you will see the quasi-normal reading. So the amplitude of wave. And after some time, because this is exponential decay, you will then see the tail, which is Apollo. Okay, so in the linear order, already there are three kinds of signals. We have good understanding of the quasi-normal modes. The tail part, I think there are very active research in the recent couple of years about the tails. And the right part, I mean, we know it's there, but we don't have a good mathematical description even now. Okay, but I think in the signal, all three types of signals are there. If we want to look at nonlinear orders, right? So as I said, you want to expand your signals systematically in powers of epsilon, right? So one good way of understanding them maybe something like this, right? So for example, in the linear part, in the linear order, the Green's function can be decomposed as the dual part plus quasi-normal plus the tail, right? So there are three pieces that together give you the total Green's function. But then at the second order, epsilon square order, so you are thinking about two, right? So two waves interacting each other, giving you a new wave, right? So this can be, for example, two direct parts interacting with each other, or two quasi-normals interacting with each other, giving a new wave, two tails, or direct part with coupling with modes, direct part coupling with tail, or modes coupling with tail. As you can see, now we only have this piece understood, which is the quadratic modes. or it's in general, it's the quadratic coupling between modes. Okay. All the other pieces are not understood. I mean, this is not to say that all of them should matter or should be important in the black hole ring down, but they should appear the same order in the ring down. But maybe some of them is bigger in amplitude, some of them are smaller. But I think it's important to characterize all of them so that you know which one is important, more important. And if they're important, you should be able to describe them. Okay. And at the third order, you also have these kind of couplings. I think their works talking about why third order effect may also matter. I will not go into there, but I think uh, 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 in principle, people can try to develop theory also at this order and try to look at the dominant effects there. Okay. So I would imagine, right? So because we will have uh very good measurement, so that for these different types of signals, so we should try to come up or construct the complete waveform model that includes all these signals, whether it's modes or it's non-modes or different kinds of nonlinearities. Okay, so with this complete waveform model, right? So you're no longer only talking about measuring the frequencies of mode, but you're describing everything in the ring down, all the important physics in the ring down. Maybe then it's reasonable to expect that with this uh, complete ring down model, maybe you can start to fit the ring down data, let's say from the peak, from the very beginning, without the need of worrying about contamination from the nonlinear effects, right? So because the nonlinear effects are incorporated. So I think that's probably it should be the way to go in the future. I think I mean there are definitely many gaps to fill. I mean, especially theoretically, we have lots of things, lots of unknowns. But I think I'm optimistic that can be done in the future. Okay, so with that, I'll conclude that I think the black hole ring down, right? As I said, it's a major evolution stage in the mergers, binary black hole mergers. And the black hole spectroscopy is about measuring the frequencies of the decay rates of quasi-normal modes. It's pretty well understood. But then I think, especially in the recent couple of years, people are trying to understand the non-modal part of the gravitational wave signal and the nonlinear signals. And with these efforts, at the end, I think hopefully we will have a complete ring down model waveform that will allow us to, right, um, measure all the important ring down signals and right from the merger peak, let's say. And I think that's important both theoretically. I mean, so we will be able to understand all kinds of nonlinearities in the theory of general relativity, also observationally. That means we will be able to understand better data much better. So I think that's the way to go. Okay, so I think I'll stop here. Yeah.
Thank you very much for the very nice talk. Are there any questions from the people in the audience? Okay, since there seem to be no questions yet, I have a question. I mean, you explained that, or let's say how I would say the advantage of considering these quadratic modes is because we just have to put together somehow the linear modes, right? And so computing the frequencies and so on is relatively easy, but how about the amplitude of these quadratic modes? Are they also composed just of the amplitudes of the linear modes, or are they independent? And like, how do we get the amplitudes for them?
Right. So yeah, so if you look at how these quadratic modes are generated, it's sourced by the coupling between two linear modes, right? So if you look at the wave, so left-hand side is a wave operator that operates on these quadratic modes, and the right-hand side is a source term that's bilinear in the linear mode amplitude. So schematically, you can say that if you increase twice the amplitude of linear modes, the quadratic mode amplitude will be increased by 4 times. So right. But then like what I explained earlier is that if we know exactly the amplitude of these linear modes, how do we compute the amplitude of this quadratic mode? So that requires especially for the curved black hole, the developments of second order Tokos equation, and that eventually will allow you to compute the amplitude of these quadratic modes, which are totally determined by the amplitudes of the linear modes. Yeah.
Okay.
May I ask a question?
Sure.
Yeah, first of all, thank you very much for the nice talk. So, I think in one of the slides, I think it's page 32, where you showed in the linear level there are three parts of signals, like direct part, tail, and modes. So my question is about like what physics controls the transition from the modes to the tail? I mean, for example, on the figure, on the right figure, you have three different curves, but they transition to the tail happens at different time and different amplitudes.
Right. So yeah, so very good question. So the temporal dependence, especially for the amplitude of these modes, uh, decays exponentially in time. Okay, so this is an exponential dependence.
Yeah.
But for the tails, they have power law dependence. So initially, the mode has much larger amplitude, but because they decay faster, so at some time, the tail will take over because they have power law dependence. So so for different systems, and the transition will depend on how much each part of the signal is excited. Okay, some so here I think different curves are representing E, the eccentricity of the plunging particle, something like that. So different eccentricity, you have different initial amplitudes of these signals. Yeah.
Okay, I see. Thank you.
I see there is also a question in the chat from Frank Lin. The question is there a way to determine the weights of different quasi-normal modes in a ring-down waveform?
Yes. So if you know your source terms, so for example, if you know the trajectory of your object, your black holes, you can I mean you can use that to like let's say in the black hole perturbation perspective, the wave is generated by the convolution of the Green's function and the source. So let's say the source is known because we know the trajectory, and then this convolution will give you the pole part, which are the quasi modes, and basically the weight of these quasi modes will be proportional to the residue of each pole and also the integration of the source term. So I guess the short answer is yes. So if you know the source term and the residues, then you can determine the weights. Yeah.
But the the point is like in the rundown, what is the source? How do we determine the source?
So in the
source should be coming from the initial condition at the merger time, right? So do we have a way to do that?
Right. So I'm talking about this problem from perturbation perspective. So which we have good control. So I'm trying to imagine a big black hole. Here I have a point particle plunging into the big black hole. So I mean in this case the particle has mass much smaller than the big black hole. So it's a linear perturbation. Okay, so in this case, if you know the trajectory of this particle, then you can totally determine the source. So then to more general scenarios, well, you have two black holes with comparable mass, mass ratios, etc. So then you have more complicated scenario because you have nonlinear effects, right? So you will need to work out all these nonlinear contributions and add them together. But at the linear order, I think this is understood. Yeah. So here I'm just presenting the linear order understanding. Yeah.
Thanks. Yeah.
You mentioned that there are multiple classes of second order modes, and that if I understood correctly, we do not know yet how strong their contribution is, let's say. Is there can you think of a strategy how we can figure out which modes, which types of mode we need to focus on first?
Oh, so yes, yeah, actually I missed the slides here. So in this paper we actually computed the different, well, there are infinite second order Poisson modes, but you can rank them by their, let's say, amplitudes of excitation or something like that. So we computed a few most important ones, and we have fitted formula for the amplitudes in the table. So in this plot, I only presented the strongest one, which is 2 times 2, but there are several subdominant second order modes there. They're also detectable by third generation ground-based detector and LISA. So yeah, I think I forgot to include more figures, but yeah, the conclusion is that if you compute all these coupling coefficients, there are at least 2 or 3 second order modes that's probably relevant for Cosmic Explorer, but for LISA, there are many more, and there are many second order modes that are relevant for LISA. Yeah.
How many? Are we talking like of order 10, order 100? Like, what do you mean by many?
Probably 10. Yeah.
Okay.
So some question about your tail. So in the later time, the tail part amplitude seems to be decaying as a power law. So that's much slower than the usual quasi-normal modes damping. So what is the physics origin of that tail part? There is some competing factors, and somehow in the later time, tail part is coming more dominant. Or what is the physical reasoning?
Right. So the Poisson modes, they can be understood as, well, intuitive as waves like trapped, well, not perfectly trapped, but trapped near the light ring of the black hole. And as it circles around black hole, the light bundle expands so that the amplitude decreases in time. I mean, the decay rate is proportional to the expansion rate of the bundles. It's a so-called Lyapunov exponent. So the tail is that as you shoot waves towards far away observer, it will, I mean, far away from a black hole, the space-time is not flat. The space-time, right? So it at least has an m over r piece in the potential. So the waves will interact with that potential. Okay, so the interaction of it will continuously scatter by this 1 over r potential, and the scatter wave will reach your observer later on. So it turns out that this kind of scattering will generate power law dependence in the received signal.
And another thing is, what is the non-modal contribution? What is the meaning of the non-mode?
Okay, so you see in this signal there are 3 parts. Only the poles are the quasi-normal modes, but both the direct part and the tail, they're not modes. They're not signals that has this oscillatory decaying oscillatory sinusoidal behavior. So by non-mode, I mean this direct part and tail. Yeah.
Okay, thank you.
I have, there are 2 more questions here, I think. Like, one is, you talked about the direct part as being the initial part in the decomposition of linear signals, but this initial stage is likely nonlinear, right? Hence, how can we describe this part nonlinearly?
So this is, even in the linear calculation, so if you have a black hole here, I throw a particle into the black hole, right? So this trajectory of the particle will already generate direct signal. So as the particle moves, it already try to radiate gravitational wave that comes directly towards the observer. It doesn't have to resonate with the black hole and then come outwards. So the part that resonate with the black hole and come afterwards are the quasi-normal modes. And this particle, as it moves, it already shoot waves already. From the light cone, right? That's the direct part. So even in the linear picture, there is already the direct part that arrives at the observer first. You don't even need to have nonlinearity. Of course, if you consider binary black hole mergers, like Campbell mass ratio binary black hole mergers, then yes, then the direct part has both linear and nonlinear pieces, right? So the direct part of the signal, they will interact with direct part of the signal and then at different orders, and then they will generate new signals. So as I try to argue here, right? So these kind of couplings have never been discussed and computed, but they may be relevant if you try to describe the ring downs, because I believe they're all present in the ring down. Yeah.
Okay. And then there is a second question. Thank you very much for the nice talk. People have been suggesting that small bumps in quasi-normal modes effective potential could lead to the emergence of unstable, long-lived quasi-normal modes. What would be the role of nonlinear quasi-normal modes in this type of analysis?
So the question is, what would be the role of nonlinear quasi-normal modes in that? Okay. So there okay. So there are many studies, papers about the so-called spectrum instability. Okay, so the simple argument is that if you have a potential, so let me show you a potential. Okay, so if you look at such a potential and you solve the wave equation, and let's say if you add a bump on the potential here, a very small bump, and you solve for the quasi-normal modes, and then suddenly you find some of the mode frequencies change dramatically, even if you have very small bump. So this just reflects the fact that the Poisson mode, this eigenmode description, is very susceptible to small changes. But on the other hand, if you look at the time domain signal itself, right? So if you have a small bump, you work out the time domain signal of the ring down, it barely changes at all. So, I mean, the mode description changes a lot, but the time domain signal hardly change. How do you reconcile them? Well, there are different ways. You can still try to use the new mode basis to understand the new time domain signal that may require you to sum up many more modes, or you can use like a perturbed Green's function and this kind of approach. Well, the Green function itself is only weakly perturbed. It doesn't get strongly perturbed by a small bump. So I would say there are many ways of dealing with this so-called spectral instability. I prefer to use more robust descriptions. Yeah, as for the nonlinear modes, is the same thing. So if you want to discuss the effect of small bumps to nonlinear modes, I would suggest not to do that, because working out the new mode spectrum and try to sum up all the mode is, I mean, I'm sure you will get at the end you will get the same result, but it's not the most economic way of understanding the ring downs. Yeah.
Okay. Do we have any other questions? If not, I think we can thank Huan again and give him a break. There were already quite a lot of questions. Many thanks for the nice talk.